Kappa Phi is not a fraternity or sorority. It is an honor society. Membership is not granted to all, but must be earned. Phi Kappa Phi members at North Dakota State University truly are among the brightest and highest achieving students in the nation. At a university known for its tough standards, NDSU students invited to join at this level of academic performance typically represent about 3% of the university's student population. The Phi Kappa Phi faculty lecture was established in 2015 by NDSU President Dean Bresciani to recognize faculty whose outstanding high-impact research, scholarship, or creative activity consistently supports NDSU's top-tier research status and who have a proven ability to effectively present their research to a broad community in the land-grant tradition. Tonight, I congratulate each of the winners of the Phi Kappa Phi Lectureship Award. Dr. Bill Wilson, Distinguished Professor of Agribusiness and Applied Economics, will be given the second Phi Kappa Phi lecture on February 16th of next year. And Dr. Mukund Sibi, University Distinguished Professor of Chemistry and Biochemistry, about whom you will learn more later, will be giving the lectureship this evening. I also want to thank Jean and Bill and Green, Vice Provost for Faculty Affairs and Equity, who facilitated the selection process and the arrangements for tonight's presentation. After Dr. Mukund's presentation, Dean Bresciani, President of North Dakota State University, will also offer some brief remarks. And now, please welcome Dr. Kimberly Wallen, Dean of Science and Mathematics.
Thank you very much. It's an honor to be here this evening. So actually, Dr. Gregory Cook will do the introduction this evening. He's a longtime colleague and friend of Dr. Sibi. But before he does that, I wanted to take the opportunity to say, I've been here for about 1.5 years, and the first time I met Dr. Sibi, I didn't know what to expect. I knew that he was very well accomplished. And one of the things that struck me and has stayed with me is he was so very kind. He was very generous in the information that he shared. He was also extremely patient with me as I asked many questions about him, about his program and his background here. And since that initial meeting, whenever I've brought up his name or his research to people within NDSU and in the research community, undoubtedly and always, one of the first things people say is, what a kind, remarkable human being. And so with that, I just wanted to share that because he will talk about his research and you can read about his many accolades, but knowing that warm, generous spirit, I wanted to share that. And with that, I'll invite Dr. Cook up to do the introduction. Thank you.
Thank you so much, Dean Wallen, and thank you all for being here this evening. It is really an honor and a privilege to be able to introduce my colleague and friend, Professor Mukund Sibi. I've known him for the 25 years I've been at NDSU, and his career spans longer than that, I think 33 years now, correct, Luke? Yeah. I could stand up here and tell you about all of the things that he's done for NDSU, like bringing in close to $55 million in research funding through various means to NDSU, the 250 undergraduate students he's personally mentored in his research laboratories, not to mention the thousands of students he's taught in his classes, 70 graduate students, 66 postdoctoral fellows who all worked with him in research. But I can point you to the handout, the brochure, the information on his bio to get a lot of information about all the things he's done. I think what really exemplifies Professor Sibi is a quote that I actually want to read of his. And this is upon the occasion of him receiving the Arthur C. Cope Scholar Award, which is one of the highest awards for organic chemists in the country, and it's an international award. And so when he was awarded that in 2008, his comment was, "This is indeed a big honor. I am very happy that our department has received this recognition. Like any researcher, it is a team effort, and credit is also due to the talented group of undergraduate, graduate, postdoctoral students who I've had the privilege to work with over the years. Okay, and I want to reiterate this. I am very happy that our department has received this recognition. I think that speaks volumes about his character, his philosophy, and his 33-year career here, because he wasn't thinking about himself. He was thinking about how this will elevate all of us. And that is what exemplifies everything I've seen from Mukund. From the day I came on a snowy March day to interview, and I met Mukund for the first time, I saw that then, and I saw it every day since, and I continue to see it now. So I'm not going to take up the time because I want him to talk. I think his passion for research excellence and his interest in helping elevate everyone around him screams about the excellence that he asks of everyone around him as well. And I think that's evident that he has made huge impacts across the world, one student at a time, one colleague at a time, and one molecule at a time. So please help me welcome Professor Mukund Sibi to the stage.
Thank you very much, Greg. Thank you. Thank you, Dr. Warren. Thank you all for coming to the lecture. And thanks to the selection committee for giving me this honor, the PKP lecturer. And it's humbling because, you know, getting selected for something is always a humbling experience. So what I hope to do today is to kind of give you a glimpse of what I have done in research in the last 30 years here at NDSU. Nothing in any detail, so don't worry. I won't ask any questions at the end. There will be some structures as chemists do, but I will more or less kind of interest spread what I have been interested in doing in NDSU as part of my career. And so I am a synthetic organic chemist. And so that means I like making molecules and a variety of them. And it's organic in nature. Organic made of carbon, hydrogen, nitrogen, oxygen, and other elements, which are we all are made up of the same thing, and all of the things we use every day are made up of these elements. And organic chemists tend to use these elements in creative ways to kind of address global issues, whether it's the medicine, what we are now in the COVID era, it's an important issue. How can we make better therapeutics? Or the seat you're sitting on, how do you make it comfortable? What kind of plastic? You know that every day we use a lot of different things. So I want to connect these two very different parts of what we do every day. Medicine to materials. No? I have to stand here?
Yeah, unfortunately.
Oh, that's too bad. I know otherwise you don't see the picture either, but nobody needs to see my picture. But okay. Anyway, there goes my wandering around to giving my lecture. But okay, let's look at my first slide. Awesome. Okay, this is the two worlds I want to talk about today. One on the right-hand side, as you can see, is how organic chemistry can impact on medicine. On the other end of the spectrum, how organic chemistry impacts on the material parts of the world, that are things we do use every day. And what I'm really interested in today is to bring about this intersection, like the Venn diagram, this in-between portion of the how these two really intersect, whether what kind of science we do here or what kind of science we do here, and the important part is the middle part of the picture. That is, we really want to create new science. I mean, obviously, if you're a scientist, you want to make the best contribution, the most interesting contribution, the most important contribution. So that's what we train our students in, how to engage in doing state-of-the-art science. With that, so this is not, just doing science has a lot of other components to it. One is really capacity building. There is a human capacity building, whether it is a high school student who comes to work with you, or a graduate student who comes to work with you, or a postdoc who comes to work with you, and training them, educating them, and making them enter the workforce. So capacity building occurs in many different ways. It could be infrastructure, it could be human infrastructure. And most of the time we are interested in the human infrastructure part of the capacity building. So I want to kind of, as I talk through my science, I want to highlight some of these aspects of infrastructure, human infrastructure, research capacity. Obviously, we would like to do economic development. So when we do science, we think that hopefully we can address some important parts of how our new science can address issues related to economy, state economy, regional economy, as well as global economy. I have a phrase here, grow ND. So this was an idea we had, which would incorporate all of these things. It's growing North Dakota, how science, the science we do could impact on the economy and other aspects of North Dakota. I won't touch too much on it. It's still something we are working on along with my colleagues, and hopefully we will be able to tell you where we are the next time I give a lecture like this. So one important component of all of this, whether you have a high school student or an undergraduate student in a laboratory, one key aspect of science or other educational component is mentoring. Mentoring occurs in many, many different ways. And I learn from my colleagues every day. I learn from my students every day. So it is really, and then there is this symbiotic relationship. You mentor the student, they mentor somebody, another student or a high school student. So this is critical to what we do in any of these intersecting part of the slide. So hopefully that will also come through during the presentation today. Okay, it's a little bit of chemistry. The thing I'm very much interested in doing organic chemistry is something which we all know we are part of, which is what we call as chirality. So chirality is this is just a normal tetrahedron which has four corners attached to four different things. So when you put a mirror in between it, the mirror image will not be able to superimpose on that original image. So these two images are molecules in chemistry are called enantiomers. So this is a concept and this is a physical phenomenon. These are indistinguishable in any physical way except when there is another chirality is present, another chiral molecule, for example. So this concept is pervasive in the science I have done. So I just want to introduce this to you. These are molecules called enantiomers. You see them in, for example, in our building blocks. These are amino acids. This is what our proteins are made of. This is an alpha amino acid, and that carbon has an amine, carboxylic acid, some other function. So all of the 21 proteinogenic amino acids we have are made of these building blocks. So I was interested in this, not in just using them, more like, but also a slight variation of this alpha amino acids are called beta amino acids. So now if you look at this, this is a location issue. So this amino group is 2 carbons away from that carboxylic acid. When I was a postdoc, my postdoctoral advisor made Taxol. And so Taxol became a big therapeutic, cancer chemotherapeutic, especially for ovarian cancer. And when I was in his lab, since that particular Taxol has this kind of amino acid as the key structural unit for its biology. So when I came to NDSU, I said, oh, maybe this is an area of science which was really not that popular that I should pursue. So I was interested in using amino acids which are readily available. But at the same time, one thing I really do wanted to do was to look at compounds which could be therapeutics. So that was my initial focus was medicinal chemistry. So how can I build organic molecules relatively efficiently, and also using this kind of a thematic idea that I wanted to build molecules of this type using amino acid building. This particular compound, which is called slavamine, it's everywhere. It has a local impact because when cattle eat this fungus infested wheat, they actually lose all of their muscular control. So there is economic issues related to this particular compound. So we actually built this molecule in our lab using 2 amino acids, a serine and a proline. And so that was actually quite interesting. And on the other hand, at the same time, early 90s, the human immunodeficiency virus, HIV virus, was very prevalent, and there was a lot of interest in looking at the compounds which would be able to use as a therapeutic. And this particular compound called castanospermine, isolated from castor beans, was a potential therapeutic. So we made molecules of these types in our laboratory at that time. And this is a sugar enzyme inhibitor. So it kind of gives you an idea of the types of molecules we were initially interested in. But more so, in going away from this theme of using naturally occurring amino acids, we wanted to develop compounds which were unnatural amino acids. So what we don't find in proteins, non-proteinogenic amino acids. The reason being that they have good potential for a lot of other things. So when you incorporate them as part of a therapeutic, these are unnatural. So when they are used as a therapeutic, they won't be easily broken down because they are normal amino acids are recognized easily, whereas the unnatural amino acids are not recognized. So you can make useful therapeutics from them. So this is a a mimic of a naturally occurring amino acid called phenylalanine. So it has two phenols. And we also did a lot of beta amino acid chemistry, which I won't tell you anything about. So many of them have been patented. So this was my first early patent, which was commercialized actually. Aldrich Chemical Company sold this particular compound, a compound derived from this for a while. Although I didn't make any money, but it was still, the university made a little bit of money, but not a big seller, not like my postdoctoral advisor who ended up making $500 million for his discovery of Taxol. So commercial aspects of your science, but I didn't really know when we originally made this particular amino acid. I didn't really know how much an impact it would have on my science. It's kind of made everything I have done from then on in one way or the other. And so this particular compound, we were interested in at that time to do chemistry, organic chemistry. And the idea was that in order to do organic chemistry involves making carbon-carbon bonds. And there are many ways to make them. And then we use some kind of a reactive intermediate, or how to, two reactive intermediates of opposite polarity, for example. Anion, meaning a negatively charged intermediate, a positively charged intermediate. And but my interest at that particular time was to do chemistry with an intermediate of these two, a single electron containing reactive intermediate. We call that as a radical in organic chemistry. So how do you engage these kind of intermediates in making new carbon-carbon bonds? And I want to take you back to my original idea, because I was interested in making compounds which were chiral. So I wanted to make that carbon-carbon bond in a stereoselective fashion. So this was an area which I had really not that much experience in, because most of my chemistry had, my training was all in carbanion chemistry, but we were interested in this radical chemistry. So this was approximately 1994. So things happen very rapidly. So I want to make a new carbon-carbon bond. And this is the kind of compound you saw when an unnatural amino acid I was talking about before. Don't worry about all of these details. I'm not interested in telling you any of those, other than to say this particular compound we made in the lab was super essential for bringing about this new carbon-carbon bond formation in a very high efficiency, stereochemical efficiency, how they interact, how they are made, either as one enantiomer or not. So at the same time, one of the things which we kind of inferred from our chemistry was that there is a catalyst which one needs to do this reaction. And the catalysis is something which has been throughout my last 34 years of science. And there is all aspects of catalysis, and I will show you couple of other ones as we go along. And the biggest discovery here was that for radical chemistry, to use what we call as a metal-mediated catalyst. In this case, this is a magnesium as a metal, or a terbium. This was a big discovery, and it was so for the first time we were able to demonstrate that these radical chemistry can be used to make very highly stereo controlled bond formation. So I said one of the key things I want to do today is to tell you about the human impact, not just the scientific impact. This is Dr. Jinghua Ji. He came to my lab from Shanghai, very small, 5 foot, but barely. Super chemist. He always had a smile on his face, and now he's a senior research fellow at Abbott, scientist extraordinaire. He was responsible for some of the early discoveries from our group on radical chemistry. And he actually, I will connect him to another aspect. So many of my students end up working at big pharma, and senior research fellow is the top honor in Abbott for in the scientific ladder, not the corporate ladder. So, as I said, things were happening very, very rapidly. One of the things which these are 3 very famous scientists. Dr. Dennis Curran from Pittsburgh, Dr. Porter from Vanderbilt, Bernd Giese from at that time University of Basel. So they are kind of the gurus of radical chemistry. So this was that, but they wrote a book on stereochemistry of radical reaction. This was a quote in the book that enantioselective radical reactions are not known. But by the time the book was coming out, we had actually done the first enantioselective radical reaction in our laboratory. And that kind of looks like this. It's very similar, to the chemistry I showed you, but this involves a catalyst, a chiral catalyst, containing a chiral entity, and magnesium, as I showed you before. And so we were able to demonstrate that we can make new carbon-carbon bonds with very, very high selectivity. So within a period of, say, 1994 to 1996, we published like 10 major papers in major journals demonstrating this chemistry with free radicals. And it was and it is still, it was kind of the holy grail in radical chemistry. And that's even today, wherever you go, people recognize you for this. So another interesting tidbit about human impact. At the 1995, I have a student from Morehead State who was a Fargo resident who came to my office and said, I want to come and do research in the lab, undergraduate. And so I said, yeah, sure. I'm always open for students to come and do research. And dynamite. She was one of the best students I have had in my laboratory. And she has a lot of number ones, which goes with her. She's currently vice president Verona Pharma. While she was at GlaxoSmithKline, she discovered this anti-tumor agent, cancer chemotherapeutic, which is now on the market. And so this is what I say about mentoring. When she was a student, she wanted to quit when she was I want to get a master's degree. That's what she said to me. She said, you're so talented. There is no reason why you should not get a PhD. And finally, she said yes. She went on, and then now became quite famous. And she was the first NSF graduate fellow at NDSU. And So many accomplishments. And I'm very proud of her as a collaborator in my laboratory. So I once again go back to this word catalysis. Some of the two things I showed you today are metal-mediated catalysis. Metals are associated with toxicity. So there is a whole new area of science called organocatalysis, which means use organic compounds instead of metals to make the reactions go faster. In this case, if this catalyst is chiral, then you can do the same kind of a chiral catalysis. So this is something also we do in our laboratory, and this is now, if you probably read the newspaper last couple of months, this was the theme for this year's Nobel Prize in Chemistry. And so we were one of the first ones to do a radical reaction using a chiral organic molecule, making this carbon-oxygen bond. So the Nobel Prize winner and I were competing at the same time for this science. He's brilliant. He's done very well. And so we are also we also did the chemistry at the same time. There are other things which we have done. One of the interests I've had is making enzyme catalysts which look like small organic molecules, which function as a catalyst, very similar to enzymes, enzyme mimics. And so we have developed a concept of chiral relay, which I won't tell you in detail, but one of the focus is to prepare these small organic molecules, which essentially behave like enzymes. Instead of working in water, aqueous medium, they will work under organic mediums to do organic applications. So other areas of interest for us was using these chiral relay templates. We made many natural products. I don't focus on natural products, although in our group, we probably made 150 different natural products over the last 30 years. But I just show you that one of our accomplishments is to develop these new, they're not new, but dipolar cycloaddition chemistry to make heterocycles, which are molecules containing heteroatoms, which are very prevalent in almost all of the therapeutics. Our ag materials, agricultural insecticides, fungicides, etc., contain these kind of molecules. So going back, so once again, one key contributor to my science at that time was this student from Bismarck, Levi Stanley, who is now a professor in Iowa State. Another kind of an interesting story. So I get a call from a student from Hopkins and says, I want to come and visit you. I'm currently a grad student in Hopkins, but I want to come and visit you to see if I can work with you. I said, student from Hopkins wanted to quit Hopkins and come and work for me. I said, why? I said, I'm homesick. So I want to come back to Fargo. And although he's from Bismarck, his wife was from Mohan. And so he came back, and I would say one of the best decisions he did, and one of the best things that happened to me, because this was an awesome student. And his career now proves that he's done all of those very well. So another interesting Fargo, North Dakota connection. While all of this was happening, I have to probably speed up a little bit, I assume. One of the other things which happened, 1999, Dr. Bushak, who was at that time VP for research and came in and said, "Oh, we have an opportunity to apply for a center from National Institute of Health and for establishing biomedical center for biomedical research." So this was a great opportunity, and it required a person with funding from NIH and also somebody who could lead. We assembled a team, including my colleague Greg and many others in chemistry as well as pharmaceutical sciences. And it was crazy. It was like we're writing proposal in 3 months for this, and we got funded. We got funded for the first time, for the first go around, and that was 2001. And so this center now is in from 2001 till today. It's now the funding has ended, but we still have 4 facilities as part of the center. Kind of give you the other dimension for capacity building, and I only talked about grad students. The theme for us was cancer. This was a class of enzymes called matrix metalloproteinases. I will skip that. And this is kind of the outcome of this center for the last 19 years. 40 faculty from different departments throughout the campus were part of the center. The center itself got $27 million from NIH. So, and this is the ROI, $75 million from grants from different faculty who were part of the center. 550 publications and many patents and other things I don't discount. And Dr. Sankumali now is another corporate PI who's one of the original junior investigators in the program. Another dimension which I didn't really don't capture this one all the time. 30 of the faculty went on to get promoted either to associate professors and to full professors. So this was an important part of our part of the center. And the last week before research was the members of our JHU was part of the center, and as I said, the whole which were established. So science lead to very different aspects, and many of these, I would have to say, mentoring has played a very big part in achieving many of these accomplishments. So mentoring plays a big part, and also the scientists themselves make all of the their own accomplishments. A couple of things which came up. So as we were going through the program years, one of the things we were interested in early on, many of you may recognize, these are flax flowers. This is flaxseed, and this is one of the compounds we made in our labs. Flax is a unique, it has a unique relationship between NDSU because our first president, Professor Dr. Edwin Ladd, was a big scientist. He investigated linseed oil made from flax. First president. And it also has some interesting therapeutic benefits. So this we excrete in urine. This compound is used as a marker for chemopreventive protection, in the sense that we from the food pyramid, eat more fiber. It's good for it. And what is fiber? Fiber is one particular type of fiber which is present in lignin, gives you in flax, gives us the most amount of enteromatic. Another interesting correlation Katie Randell, who is a faculty in biology, now works on molecule enterolactone and another compound called hyperlanolin in terms of cancer nutraceuticals. So the interesting compound for biology. So other biological aspects, which I will skip over. This is something we were very much interested in. We still are in looking at triple negative breast cancer therapeutics for triple negative breast cancer. My current program is a collaboration between myself and my colleague at UND on making new compounds for prostate cancer. So let me kind of, in the next few minutes, tell you a little bit at the other end of the spectrum. That is the Center for Sustainable Material Science. And, so let's go from one way of medicine back to material science. This is a program which Dr. Webster, who is in the audience, and I lead, was established through an EBSCO program. And the goal for this particular program is to use renewable resources, biomass in general, and then use them as a feedstock to prepare monomers, building blocks for polymers, just like my amino acids, which are building blocks for proteins. And also to then make convert these monomers into polymers, or use this biomass to make composites. And then one of the key things to this particular program was what we call as a cradle to cradle approach, meaning we want to close this loop where we go from biomass to polymers, and then degrade the polymers back to the monomers, so that we can we can reuse our building blocks. So that was a kind of the unique nature of this particular program. But this is now in the 2000s, but this whole concept of using renewable resources to replace fossil fuel-based chemicals is has taken on a new dimension in the last 25 years. And a whole new areas of science and thinking, what we call as green chemistry now. And it has many, many interesting and important ideas behind chemistry. Our new undergraduate program for summer undergraduate programs based on green chemistry. So use of renewable feedstock, catalysis, the same idea you saw before. Another key concept I will show you is degradation of plastics or polymers at the end. So many key goals or key concepts to make things better and to address some really global issues related to waste prevention and other things. But my involvement in biomass really goes back to another 25 years ago. If you go around in North Dakota during summer, 4 years, you see a lot of this beautiful yellow fields. This particular is canola. And at that, in the early 1990s, the USDA wanted to have a program in genetically modifying rapeseed or canola into a crop called crab. The idea was that cranberry can be grown very well in North Dakota, high yields, very little anything, no issues with any kind of insects. They were easy to grow, and just like many other things which we grow very well in North Dakota. there is some uniqueness to this particular oil seed. One of the three components of biomass. And the key thing was that this particular cranberry produces in its oil has 70% of a single compound called erucic acid. The erucic acid has 22 carbons. And so humans only digest fatty acids of 20 carbons or less. So this is not a oil which we produce for cooking because we don't digest it. So the idea was here, what can we do with this particular crop, which grows so well? Can we use this as a feedstock for chemicals? So that was the idea. So the goal was to find what else can we do with this particular compound. And so the earliest thought at that time we had was, okay, maybe we can break this one down, break this erucic acid into two smaller components, with the goal of doing this in a process in a catalytic fashion. So this particular transformation, you can do this in industry practice. It uses ozone. Ozone is not very cheap. It's pretty expensive, and handling ozone is quite touchy. So what we were interested in, to develop a process which uses molecular oxygen which we are breathing now. If we wanted to use that, we use a catalyst so that we would be able to prepare this building block. Now, this is a dicarboxylic acid, which are common precursors for making nylons. So this was our first go around, and so we were able to demonstrate, yes, we can make this quite effectively, and but it still had its problems. Come back to the same kind of our human issues. So one of the first undergraduates to work on this particular project is Dr. Mary Jean. She was an NDSU undergraduate. She, once again, she was in my class, and she said she wanted to do research. I said, yeah, sure, great. So, and now from Berkeley, she was originally, and now she's the director of R&D therapeutics at Eli Lilly. So the undergraduate training really does matter. So she's a part of the COVID program at Lilly, directs the COVID program. And so anyway, a couple of years goes on. This is now 2008. So we wanted to do this with no organic solvent. So we wanted to develop a method which was totally what we would call as a green method, where we would convert this erucic acid to biochemical acid and other components. So what is good for this? We can make nylon 1313 out of this. We made nylon 1313. USDA made it in large quantities. We made this in the lab. So this is musk sand. So the highlighted portion is the ethylene glycol. So this is bacillic acid plus ethylene glycol. You can make the basic scent called, now it's commercially sold as exalkaline. And so we did this in 1993. Very proud of it. And when we made more improvements to it in 2008. Touch on the two other areas of current interest. All of you know this BPA. BPA, bisphenol A, made from fossil fuel, outstanding precursor for made in large quantities in the world. It's used for many things, and but it also has a problem. And BPA has a bad impact on so it This is estradiol receptor, the estradiol compound, and PPA mimics estradiol. So this becomes essentially an inhibitor of estradiol, and so it's now has a bad rap of being a compound, not wanting to get rid of it in almost all the materials used for as humans for when we use for things like food container coatings, plastic bottles. So we've been interested in trying to find a safer alternative to bisphenol A, something we can make from biomass, and at the same time, which have no estrogenic activity. So cellulose is any of the things you see wood material has hemicellulosic and lignocellulosic materials. They can be converted to glucose, and glucose can be converted to this key building block called hydroxymethyl. So we made several different PPA replacements, which have no biology, which show no biology. So there will be potential uses as replacement for PPA. So another demonstration of these renewable resources to use for materials. And my final couple of slides has to do with plastic pollution. You see this kind of pictures everywhere, and it's real. We have to deal with it. And I alluded to this in my initial slide about cradle-to-cradle approach, or how we can degrade materials. And so this is one of the common polymers we use to make all kinds of things, and one of them is plastic bottles. This is phthalic acid, a polymer from ethylene glycol and phthalic acid. So a fossil fuel-based polymer. So this is a furan dicarboxylic acid. So everything else is the same. This is the biomass-derived compound, and this is fossil fuel-derived. And now this is going to be made in large quantities. So this will be 100% biomass-derived material, and so people are building big plants in Europe to do this. But this doesn't really address the key problem of how we can safely. One of the things that, as you see, is that these plastic bottles, we put them in landfills, hard to degrade, takes a long time. The concept we wanted to do was to design a process where we could essentially degrade on demand, in the sense that we would incorporate some kind of a trigger into our polymer. And in this case, it's a photo trigger. And when we make a polymer, show that they are useful, they have good properties, etc., at the end of their lifetime, we could now shine light of different treatments, and then that will allow us to degrade the polymer, cleave this connectivity, and then release the building block. In this case, the furan dicarboxylic acid is solved with the plastic block. And this we have put this into practice, and so we can clearly show both in suspension, as we see here in this picture, or as a solid. We can essentially degrade our polymeric material back to the bond. So we can close the loop and then recover and reuse our we have got several more versions of this, which which is ADSU has patents on this. This is not just this is not me only. This is a collaborative effort between Dr. Jayaraman and Dr. Webster and our group. I hope I've been able to give you a glimpse of what we do in our group as science, and also all of the other things show with it. This is my current group. This was last summer. When you see, this is what you should see. My diverse, energetic group of students who participated in this science. High school students, undergraduates, graduate students, postdocs, visiting students. I thank them all for. I thank them all for. Let me close this. I thank them all for their effort and cheerfulness in doing science. And I really need to acknowledge others also, especially the team Sibi over the years. My people we have been really fantastic to collaborate with. Dr. Bushak, Dean Webster, Siwa, Brett Chisholm, who was part of the Coatings and Polymeric Material for a long time. Dr. Chad Alvin, Andre War now. Alexia Tulin is a faculty at UND. Andra Frost is my collaborator on breast cancer. I have to say I've been very, not all the time, it's been great to have support from a lot of the funding agencies. Without that, I would not have been able to do any of the research we have done over the years. So I thank them all, and I thank my students, and I thank my collaborator and you all for your attention and your patience, I would say. My watch says 8 o'clock. So thank you very much.
Thank you, Professor Sibi, for a great presentation. Would Dr. Wallen be able to help facilitate questions from the audience that's live? And if you are joining us on Zoom and have a question, you could use the raise hand feature under reactions, and I'll recognize you to ask your question.
Yeah, are there any questions from the audience? Mike?
Happened in that area this year, and you alluded to this. I'm wondering if you could elaborate on when you were working in that area and they were working in that area. Were you aware of what they were doing? Did you kind of get scooped, or what was the story there with the?
We published a very similar. Yeah, we published at very similar times, and we've been working in organic catalysis. We've done other type of organic catalysis. So, there is competition everywhere, and we still compete. But I can't compete with him right now because he's got too big a group and too many resources, which I don't have. So, but he's brilliant. It's really good.
Great, thank you.
If there are other questions from the audience, can you please repeat them in the microphone so that those joining us online can hear?
Sure. Are there any other questions from the audience? The in-person audience? Yes.
Thank you very much for the great talk. What is your mechanism towards handling a new problem? As you mentioned, that radical chemistry was not your forte from your training, but you essentially tackled it. So
it's recognition. The problem, and then you have to, an opportunity presents itself. I mean, I don't think I would have done radical chemistry because we were doing anionic chemistry. And then we said, oh, can we do this by radical chemistry? And it was not the same process. Instead of going this way, we were trying to go this way. And when that happened, we said, oh, maybe we could address this as a general problem. So it was recognizing that there are opportunities. And you got to kind of know the field. So what is known, what is not known, and take advantage. And I have to say serendipity plays a big part in science. So all the stars converged at the same time very well for me when we were doing the radical chemistry. We had the right students, and a colleague from UND moved to Morehead State. He had done radical chemistry before, I had not. So he came as a postdoc, was a visiting scientist that summer. So it was my chiral auxiliary played everything. So it was all kind of the combination, but that goes true for all the other type of problems here. You kind of have to say, okay, are these, man, yes, spam calls everywhere. So that would be my answer.
We do have a question from an online member. Go ahead.
I'm not sure if is that for me.
Sorry. Yes, yes.
Okay. So Muk, what are your plans for the future regarding not just your science, but your broader activities at NDSU?
I don't know. First, to be good, healthy. So, okay, one key component I didn't say anything about is because I have to recognize my wife, because she keeps me alive. She's everything to me. And so without her, I don't do anything. So that's number one. And I don't know, do new science or new centers, or I don't know, whatever the opportunities are. So.
Were there additional questions from the audience, in-person audience?
So a couple of questions have been written in the chat online. So first, what advice do you have for finding, developing, and sustaining collaborations?
Collaborations are, you got to like the person you work with. That's number one. But you know, I think science brings people together, and these days, I don't think it is easy to do science without collaborations. And it is the magnitude of the problems one needs to solve requires people to work together. And sometimes you're forced to collaborate, and then a lot of things come out of it. So I think that's also fine. But collaborations work well when you're, when you interact well. So people skills are important.
Were there other questions in the chat?
I think it's.
Yeah, there's one more. So I'll read this. Since molecules have many degrees of freedom in space, how do you affect an enantioselective synthesis? If it is about the patterns in the molecules, would you consider engaging architects to explore patterns and structures in the abstract and how these patterns and structures fit with each other?
Okay,
Wow.
I gotta kind of show this. So, for example, when you have a flat system, you have two faces, right? Top face and a bottom face. So when you're trying to control how things approach, so if I block the top face this is how we do this with chiral molecules. So when you block the top face, so the only way another molecule can interact is from the bottom face. So you kind of control through this chiral assembly, you control how a particular species approaches another. And that determines, these approaches then determines the outcome, giving you an enantiomeric compound. So we call this compounds which are flat, are prochiral faces. So prochiral meaning approach from top or bottom will give you enantiomeric compounds. And that's why there is no chirality cannot be created unless you have chirality. So that's why you need chiral catalysts to our chiral molecules to create another chiral molecule. So it is a control of approaches is very critical. Hope that answered. Yes, Chris.
Hey, Mook, thank you. Advice for the top 3% of students and maintaining intellectual curiosity like you have throughout a career.
Say this again now.
What is your advice for the top 3% of students to maintain intellectual curiosity throughout a career? Right, we are talking about this lectureship. Thank you very much.
I don't know, love of doing science. You got to show students the excitement in, you got to lead by example. So I think when you mentor a person, if you are look very blasé, and I don't think your students will be would take that as it's not that interesting. So I know we were having this comment about students wanting different, children wanting to go to different careers as their parents this afternoon. And so I think children do that in the sense, it's the same way at home or in the laboratory. You kind of have to show that enthusiasm for life and for discovery. And I think that's what you can do that. It doesn't have to be for the top 3%. It can be for everybody. I mean, I think it is really, I think a lot of people are very reluctant to do something new, but if you can give them that, this is great, you got, why is it great? And so you got kind of lead by example. Thank you, Chris.
Got a thumbs up.
Yeah.
Are there any other questions? All right. There are no more questions from the in-person audience. Can you hear me?
Is President Bresciani present?
Yes, he is. So we'll invite the president down to make a few remarks.
I really feel like I should do something with this. I don't know what it is. I want to thank everyone for being here. It's still very awkward because we've got people in the room, we have people online, and most importantly, we don't have the students here. And you may ask why I bring up the students. Back in 2015, why we created this lectureship, I was concerned about two things: Phi Kappa Phi strong chapter, very active student organization, but I wasn't sure that they were getting what the whole picture is. We often talk about being a student-focused land-grant research university, and while students are important, I sometimes find it ironic that we put research at the end of that. Because what we do is create the new knowledge that our students will need in the future to be successful. Knowledge that's never been known to humankind. That's the unique thing that our kind of research university does. And I wanted our students to understand that that is a full circle. You don't just grab some knowledge and become educated. You need to be creating knowledge, constantly creating knowledge, new knowledge that is going to be creating what we understand of the world around us in the future. And so in 2015, we started this lectureship to recognize premier NDSU faculty members who are creating that new knowledge and for students to understand that continuum. And so for having them not be here tonight really is kind of heartbreaking to me. Nonetheless, it also reminds me why we started this, the extraordinary research that's taking place at NDSU, the extraordinary researchers, and the opportunity to recognize a friend who I have known literally since I came to NDSU in 2010, the extraordinary work he's doing. To recognize that is incredibly rewarding to me. But what I really want to recognize is his closing slide, which makes my exact point. 70 graduate students, 68 postdocs, over 250 undergraduates, and 14 high school students are involved with him right now. And he honored them by them being on his closing slide of his award-winning presentation. Mook, thank you for exemplifying exactly what this award is meant to represent. It is an honor and a privilege to know you, sir.
Thank you very much.
Thank you, everyone.
I assume we're done.
We're done. I was waiting for Jeremy to say something. All right, well, thank you, everyone, and have a good evening. Thanks to the folks out on Zoom.